All right, so let's do an example problem here using the tensions. Something called the Atwood machine. Now, how does the Atwood machine work? Well, we basically have a pulley and we have a mass, M1, string goes over down to M2. Now, let's assume that M1's bigger than M2. So what's going to happen? Well, you kind of know what's happening. That means that gravity is pulling harder here than it is here, and so the entire thing is going to do that. Okay, and so the M2 is going to go up, the M1 is going to go down, the pulley is going to turn. Okay, so that's the Atwood machine. And I'd love to get something this simple, two masses and a pulley named after me, but most of the easy ones have already been taken. So let's do an example here. Let's assume that M1, the heavy mass, is going to be 325 grams. Okay. And let's say that M2 is going to be 311 grams. And so I want to know what is the acceleration of these masses. All right, so I want to find the acceleration. Okay. Now, so what do? Well, we look at this and we say, okay, we draw this. M1, M2, and I am going to have an x-axis that does this. So this is my x-axis. Okay, it's curved and follows in the direction things go. Now, why do I do that? Well, that means they're now both going in the positive direction. Okay, I like positives better. I mean, you don't have to do it this way, but I like positives. Okay, so I look at it and say, now in this case, that would mean that if I do a free body diagram of this object on the left, okay, so M1, I've got M1G, that's the weight. The weight is the force due to gravity. That's pulling down. The tension's pulling up, and I know it's accelerating downwards. Now, for the object on the right, the free body diagram here is that tension's pulling up, M2G is going down, and it is accelerating upwards. Okay, now I said this way is positive over here, and this way is positive on that side. Okay, so here I have my situation. Now, I know that the sum of the forces equals MA. So here I have a force M1G. T is in the negative direction, so it's minus T equals M1A. On the other side over here, T is in the positive direction, but the weight is in the negative direction. Okay, so I've got these two equations, and so I want to do something with them. So I'm going to add my two equations together. I'm going to add M1A plus M2. So M1A plus M2A. Okay, well, M1A was M1G minus T, and M2A was T minus M2G. Okay, so the T's cancel, and we have M1 plus M2 times A equals M1 minus M2 times G. So A equals M1 minus M2 times G divided by M1 plus M2. So A is, 325 grams minus 311 grams times 9.81 meter per second squared divided by 325 grams plus 311 grams. Okay, now, is there a problem that we have grams instead of kilograms? Well, no, because numerator is grams, denominator is grams, so they both cancel. Okay, so A comes out to be, after I do all the calculations, as 0.216 meter per second squared. Now, there's something else I could have done here if I wanted to. Instead of G being 9.81 meter per second squared, I could have written that 981 centimeter per second squared. That's the same thing, just unit conversions. And so the answer would have come out to be 21.6 centimeter per second squared. So now obviously these are the two same thing. And so I could do the unit conversions in the middle, or I could do unit conversions at the end. Same thing. Okay. So now, while we're at it, the next question that we might ask is, what's the tension? So what is the tension? So let's take one of these equations. Doesn't really matter which one we take. So, we can have T minus M2G equals M2A. And so T equals M2A plus G. And so T would be equal to M2, which is 0.311 kilograms, okay, times A, 9.81 meter per second squared, plus 0.216 meter per second squared. And so the tension comes out to be 3.12 newtons. Now notice that tension is actually a little bit more. That tension is going to be a little bit more than M2G. That's why M2 is going up. But that tension is a little bit less than M1G, which is why M1 is going down. And so that kind of gives you an idea. The tension is going to actually be right in between. So the question, though, is, we got this A, and the A is M1 minus M2G over M1 plus M2. Why does Atwood get something named after him like this? I mean, here we have pulley, we got mass, mass, and how does, well, let's do algebra here. G equals M1 plus M2 times A divided by M1 minus M2. Now, when you did the uniform acceleration experiment, one of the things you did was just take something and drop it. Okay, and one of the biggest problems there, getting the right answer, is your reaction time. Because your reaction time is a fraction of a second. The time it takes to fall is a fraction of a second. And so that's a huge percent error. So how do we fix that? Well, in the lab, we use photogates, which let the computer do the timing. It has much less reaction time. But in the old days, they didn't have the computers. They didn't have photogates. They didn't have the software. They had to do this by hand. So what they did was they used a very low friction pulley, a very low mass, low friction pulley, and they put these weights on here and let them go. They balanced the weight so that it took maybe 4 or 5 or 6 seconds to go down. Well, now your reaction time, which is a fraction of a second, is a very small percentage, which means you could very accurately measure A. And if you can accurately measure the M's, then you could come up with a pretty good measurement of G. And so this is how they used to do it before they had computers and photogates. And so that's why Atwood gets this thing named after him that is so simple and easy. It is only just a couple of masses and a pulley.